All right, so I got a list of things we need to do today. I got some announcements that I'll write down when I share my iPad. Is there anything happening around that people want to share with the group? Not seeing anything. Lupe, you want to share anything with the group? Remind people when your drop-in hours and stuff are?
Yeah. Remember you guys have priority on Wednesday from 7:30 to 8:30. I am there on Wednesday till 9 though. Usually that's the day. At that time I don't get that many people, but remember you guys have priority that one time.
Great, thanks, Lupe. And I want to encourage everybody to go and take advantage of Lupe and his support. I mean, he knows what's happening in class. He's here every day. So when you bring questions to him, he has the context to answer them. You know, one of the challenges of having peer tutor support at an institution, at a university, is oftentimes that tutor doesn't know the context that your question's coming from, and they answer the question the way they were taught. But Lupe has the great advantage over the other tutors in that he knows the context in which you've been learning this stuff. And he can, while that might not be the way that he learned it, he has at least an advantage to figure out how to think about things and talk about things in the context we're talking about them in class. So don't underestimate that. That's a huge value to you. So thanks, Lupe, for your work. I think as soon as I send out grade reports, you'll probably see some more business. Okay, and I'll be doing that soon. Anybody else have anything they want to share? Nothing? I'm trying to think if there's any campus related stuff that I've heard about.
Dr. Miller?
Yeah, Lupe. Yeah.
People are still having trouble with the quiz.
Yeah. So I'll say something about that too. The quizzes. That's amongst the things that I will announce. I'm trying to think if there's any campus related things that I can relay to folks, and nothing is really coming to mind. All right, so we'll move on. We'll go to course related stuff. Let me share my iPad, and so I can write down these thoughts as I share them. All right, so it's October 6th. This is Calc 1, and we're starting to get into some really, you thought limits were cool. The stuff we're about to talk about is super cool. Course related stuff. I have grade reports made. Ready to be emailed out. Okay, and the results on the reports are through Friday. I didn't add anything over the weekend. I saw people had been taking some learning target quizzes over the weekend, but those haven't been added in. When I send you a report, it's customized for you, and it'll show you how you're doing so far, which learning targets you have shown me you've mastered, and which ones you have not taken yet, and then which ones you've attempted but not shown mastery on. It will also show you there's a couple of graphics that give you a sense of how you're doing in the context of others in the class. And that's just meant to show you the level of activity that's happening. And for some of you, it's going to tell you, oh, I got to really do more. For some of you, it's going to give you affirmation that you've been doing a good job. You've been investing your time correctly. So watch for those reports. They might come out today. They might come out tomorrow morning. I just have to figure out how to send out 60 customized emails. Also, this is important. If you see any errors, or if you have any questions about them, email me. Because one of the purposes of these reports is to let you know what I know. And if some of the information I have is incorrect, I want to give you a chance to correct it. All right. So my report isn't so much the last word in how you're doing. It's just to keep the lines of communication open, keep the stuff transparent, and give you a chance to let me know if you think that we've miscommunicated or something. There's lots of information flowing back and forth between me and everybody, and it's not uncommon. In fact, it's kind of common for me to mess something up. And that, the way I do things, that could just mean I made a typo somewhere. But as long as I know that you think I'm missing something, I can go track down and maybe see where I made a mistake. Okay, so this is important. If you see any errors, I want you in the report, I want you to reach out to me. There have been some problems with the quiz access. So we've been trying to figure that out. I spent a lot of time last week trying to fix it. And last week I spent a lot of time getting emails from students saying, hey, can I take this quiz? And I'd email them PDF right away. This is, as quickly as I saw the message and can confirm that they wanted the PDF. So I was sending out a lot of PDFs that way for people to take the quizzes. That's how I know that a lot of people were taking them. I took a break from email on Sunday, so I haven't reviewed all the emails that have come in there on Sunday. I'll do that today. But good news is I think the quiz access is fixed. So if you have wanted a quiz and you're waiting for me to get back to you, I say go and fill that form out again, get that pop up with a link and see if you can get that quiz. You might try that during our break today. Yeah, but don't do it until you're ready to take the quiz. All right? If I'm wrong, if you do have problems, let me know. Okay, but I think this is the final fix. I think there were multiple problems, technology problems, and I think I finally ironed them out. So test it out for yourself when you're ready to take the next learning target quiz, and fingers crossed. I'm trying to think if there's anything else I need to tell you. I feel pretty good about where we are on the calendar, and we're just going to keep plodding forward. Today is a full class period, so we'll go for the almost 2 hours. So please remind me that we should take a break at 8:50. So that looks like it's like 40 minutes from now. And I'm looking at the material I have here, and maybe we'll end early. I'm not sure, but we're planning to go for the full hour and 50 minutes. All right, so it's been a long time since we talked. I think the last time we talked was on Wednesday. Can anybody help me try to remember what the last big idea we talked about was? And you can vocalize it or throw it into chat. Both are great. All right. Jet threw something in there. Anybody else? So Jet wrote derivatives. And I did mention that word. Okay. And we're going to dig into this today. What's another idea that we talked about?
Robert, finding the slope of a tangent line.
Yeah, slope of tangent. I see Robert threw that into chat too. So finding the slope of tangent lines and the slope of secant lines. I'm gonna stop here. I mean, there's more stuff we talked about. Some of that I will kind of go back over a little bit today, or the stuff that I talk about today will intersect with that. But I'm going to stop here right now because these three ideas are super core conceptual ideas that you need to feel comfortable with. And I'll kind of lightly go over these two today. I'll lightly go over the tangent line and the secant line. Well, sort of lightly. And then we'll, like I said, we'll dig deeper into the idea of derivatives today. So let me remind you where we are with respect to learning targets. So here I'm looking for my notes. So learning target D2, here are three things that are in the list of objectives for D2. One is the tangent problem. One is finding the equation of a tangent line. And one is the limit definition of the derivative. So I'm going to start out today by connecting what we've talked about so far with each of these 3 points. We have basically talked about the second 2 points sufficiently for you to take D2, and I'll start by telling you what the tangent problem is. It's a historical thing that's important to know about. So this is a long way of saying you should almost be ready to take the learning target quiz for D2. You should be doing a bunch of practice problems to convince yourself that you're ready to test yourself. You should be talking with classmates and quizzing one another and testing one another to make sure you understand things correctly and find areas where you have questions. But presuming that you do that, the material that we've been talking about in class is preparation for learning target D2. Learning target D3 has, I'm going to list 3 things that are on its objectives. The first one is the derivative as a function. I guess I'm going to put 4 down here. Differentiability. Sketching f prime from f. And the geometry of differentiability. Okay, so those are the 4 things that are in D3, and we will get through all of those today too. And we might even get into D4. We'll see. I'll review that at our break and see what I can say about that. Okay, so these are the objectives for those learning targets. And you'll see that we'll get through all of these today. Any questions before I get going? I'm not hearing any, and here I just found the gallery. Let me organize it so I can see all your tiles. Okay, so no questions before we get going? No math questions have come up as you've been studying or working problems? Okay, everybody ready for the next stuff? Jesse's ready. All right, Andre and Robert and Summer. Okay, that's good enough for me. Thanks for the feedback. So let me start by talking about the tangent problem. This is a little bit of history. Oh, here, and let me show you this. I'm gonna stop the share so you've got my camera. So I'm gonna hold up a book to the camera. Okay, so this is a book I have. It's called The Calculus Wars. And if you think that that's dramatic, you have no idea. It's not overly dramatic. It is dramatic because the history of the calculus is dramatic. And on this on this title page, you see there's this not equal sign. So they're kind of abusing some mathematical notation. There's two guys, two white men, European men pictured there. One of them is Sir Isaac Newton. He is from Great Britain. And the other is Gottfried Wilhelm Leibniz from Germany. Okay. They are the two historical figures that are given credit for discovering the calculus. Okay. And they discovered it in the late 17th century, like the 1670s, 1680s. Right? So they lived in the late 17th century, early 18th century. And that's when they discovered the calculus. And they did not like each other. Newton was a huge jerk, all right? And that's why there were these calculus wars. And I'll talk a little bit about that today. It's kind of a nice, colorful history in science and mathematics. So what does this have to do with the tangent problem? Well, what is the tangent problem? And so I need to share, right? I'm not sharing my iPad anymore. Here it comes. There we go. So the tangent problem was a question that got lots of attention in the mid 17th, maybe even the early 17th century. And it would, how to say this? It's basically the question of how do you find the tangent line to a curve? So given a curve, how do you find the tangent line? And I'll just tell you, last week, we in class solved that problem, right? So in retrospect, it's not a hard problem to solve, but we have tools now at our disposal that the folks back in the mid 17th century did not have. So what did they have? So back in the 17th century, let's say early 17th century, society, and let me just say like mathematicians, had a rudimentary idea of what a function was. Okay, they didn't understand functions in the same way we did. They did not have function notation, right? Their notation was very different from ours, okay? So they were not operating with the idea of a function. In fact, functions, we would call them functions, they wouldn't necessarily, were largely described verbally. Okay, not symbolically, and verbally would often lead to graphically, certainly not numerically. Okay. And it wasn't until later in the 17th century that there were algebraic, right, symbolic descriptions. Okay, but these were largely limited to polynomials. Okay, and then maybe there were some curves derived from those. Okay. So Cartesian coordinates were not in vogue at the time, still really being understood. Okay, so I'm telling you this to let you know that the context in which Newton and Leibniz was working was very different from ours. And I think the most remarkable thing is that mean, their functions were described verbally. Imagine not being able to write down in symbols the functions that we're working with. And a lot of the functions we work with now, they hadn't even discovered yet, or hadn't even codified yet. That had to come from other people later, like maybe logarithms and trigonometric functions. They probably had some sense of those. But let me just say, and I'll move on to the next thing, things were very different. So they had this tangent problem. And it was this, the problem was, how do you find the tangent line to a given curve? Okay, somebody gives you a curve and you have to find a tangent line to it. And a lot of times that curve might be described by what we would call a function, sometimes a polynomial. And so the curve was a graph of that polynomial. And at that time, the answer was given on a case-by-case basis. That a solution to the tangent problem would take advantage of some property that that function had. Okay. So let me give you an example of how that might work. So I'm going to turn the page. So consider a semicircle. So if you want to plot the graph of a semicircle, right? That's kind of what it looks like. It's not a perfect picture, but you get the idea. And how do I find the tangent line to a semicircle? Well, you can use the geometry of a circle. So if you draw a radial line that goes to the point of interest, then if you construct, like with a straight edge and a compass, if you construct the line perpendicular to the radial line, you're going to get a tangent line. Okay. With a line perpendicular to the radial line is tangent. And mathematicians of the day would have ways of proving that, and you can kind of see it from the picture. You can believe it from the picture. But this is a case where you have a special curve that has special properties, namely draw a radial line, and the perpendicular is going to be a tangent. To find a tangent line. And here, if you know what the slope of the radial line is, you can figure out what the slope of the tangent line is, so you could find a formula for the tangent line, in our lexicon, in the way we talk about functions. So what happened in the late 1600s, Isaac Newton in Great Britain, and Gottfried Wilhelm Leibniz in what we now know as Germany, but back then the nation states were different. They both came up with a technique. So they independently discovered a technique that would allow, that solved the tangent problem for all functions. Okay, and this is the technique that we ended class with last time, and we'll talk about today. So this was humongous, right? This was huge. Huge. This was huge. Okay, and it really took the mathematical community by storm. It really had a big impact because it allowed them to apply tangent lines. allowed them to use tangent lines whenever they wanted to, because they could, the Newton and the Leibniz solution worked for all functions, for all curves. So anyway, this was one sign that Newton and Leibniz were going to become immortal for some of the mathematical discoveries that they were going to make. And the idea they had is this. If you've got a function, and here's a picture I've drawn tens of times, you've got a function that goes, whose graph goes through a point, you can go away a little bit, right? Well, first, the tangent line looks like this, the red curve. And you've got a point that's on the line. So you have those nailed down, but the question is, what's that slope? And in this tangent line here, you only know one point that's on that line. You don't know any other points. So you can't manually calculate the slope of a tangent line from the function. Right? You've got a function here. Oops, let me do that in black. You've got a function here, but it doesn't help you calculate the slope of the tangent line directly. But you can use the function to calculate the formula for a secant line. So the slope of the secant line is the rise over the run. And if you put in the coordinates here or you put in the values of the coordinates of these 2 points, this one here at x naught, f of x naught, and this one here at x naught plus h, comma, f of x naught plus h, right? This becomes your slope. And then as h gets closer and closer to 0, this point right here slides down the graph, and you can see that blue tangent line. And I encourage you to try to visualize this like a little cartoon. You can see that tangent line tilting down, and getting closer and closer to the same direction as the red tangent line. Let me repeat that again, just in case I messed up. You can take this point, and as h gets closer and closer to 0, right? As h gets smaller and smaller, this point slides down the graph. And then you can watch the secant line. It has to go through this point. So as the point slides down, the blue secant line tilts and gets closer and closer to pointing in exactly the same direction as the tangent line. So if you watch the slope of the secant line as h goes to 0, you're going to get the slope of the tangent line. Right? So this was the genius of Newton and Leibniz. Watch the slope of the secant lines, and you're going to get the slope of the tangent lines. Okay. Any questions about this? If it feels like I've talked about this 18 times, that's because it's really important. Oh, somebody wants to say something? No?
Yeah.
Yeah,
so, Jen. Can you hear me, Professor?
Yeah.
Okay, so what are you writing x sub 0 th? What is that? So
all right, so
not sure what that means.
That is a plus sign. So it's the same plus sign that's there. It's the same plus sign that's there.
That's a t. Okay, sorry.
Yeah. Okay. And this x sub 0, that's I just have a subscript on my x.
Okay, got it. Yeah, thanks.
Okay. But I will, since you brought it up, let me do this in a different color. I'll do this in green. The last time I talked about it, I used a C there. Today, I'm using an X naught. Okay. So Jet, you picked up on one different way I'm talking about it today, but it's a very slight difference. And it's leading us to an idea about a function called a derivative. And I mentioned this last time too. So, here. Yeah, so I'll mention the derivative, and then we'll go and do some computations with this idea to find some tangent lines using the Newton and Leibniz idea. So if f of x is a function, and x equals x naught is in its domain, we can define a new function that takes x naught to a value we call f prime at x naught, which is defined to be the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h, if the limit exists. We call f prime the derivative of f. So what I'll do next is we'll calculate some slopes of tangent lines, and then we'll start playing with this idea of the derivative, and we'll explore some of its properties. All right, so I'm going to turn the page here, and we're going to do some examples with computing these tangent lines using the Newton-Leibniz approach. Okay. So let's calculate the equation of the line tangent to the graph of y equals 1 over x at x equals 1. Okay, using the ideas that we just, using the Newton-Leibniz ideas. So here's some scratch work. So the first thing I'm going to write down is I know the tangent line has point slope form that looks like this. Y minus y naught equals m times x minus x naught. My x naught is 1. So f of x naught is 1 over x naught, meaning that f of 1 is 1 over 1, which is 1. Okay, and f of x naught, of course, is y naught. So my equation looks like y minus 1 equals m times x minus 1. And now we want to focus on finding that m. Okay. So now m, is the slope of the tangent line, which by the definition is that the limit as h goes to 0 of my function at x naught plus h minus f of x naught all over h. All right, so this is something you've got to memorize. The slope of a tangent line, the equation for a slope of a tangent line at a point. And now let's go fill in what this means. My function is the reciprocating function. So f of x naught plus h is 1 over x naught plus h. And f of x naught is 1 over x naught. And that's all over 1 over h. And my x naught is 1, so I can plug that in. And dividing by h is the same thing as multiplying by 1 over h, so I can pull that out. Let me write that so it looks like an h. So I get 1 over 1 plus h minus 1 over 1. So continuing, I guess what I need to do next is I could try to do naive evaluation, but then I get division by 0 here, and that's bad. So I want to avoid division by 0. So I've got to simplify this. So I got to find a common denominator between the 1 plus h and 1. Well, that's clearly 1 plus h. So this, I rewrite this as the limit as h goes to 0 of 1 over h times 1 over 1 plus h minus 1 plus h over 1 plus h. So put all those things over the same denominator and then simplify. And you see that those ones cancel and I'm left with a minus h. And that's a beautiful thing because this h cancels with that h down there. And then I'm left with a minus 1 over 1 plus h. And now I can evaluate this through naive evaluation. Get minus 1 over 1, which is minus 1. So the answer to the question is my tangent line is y minus 1 equals minus 1 times the quantity x minus 1. Okay? That's how we do this. And we say that this solution to the tangent problem is by first principles. Okay? Here we're using the definition of the slope of the tangent line to find this. Last Wednesday, Robert asked a question about using some other rules and some other formulas. And those are higher order principles. This principle we're using here is the lowest one, the most basic one, the first principle. We'll see these other rules probably on Wednesday. So how can I check my work? And when you're in a math class, it's always nice to have a way to check your work. Anybody have an idea? You can vocalize it or throw it in the chat. Anybody? No? Any guesses? All right, well, let me ask you a question. All right, here, it's going to be a 3, 2, 1, go question. Okay. Do you think this is the correct answer? Right. So it's a yes or no question. Do you think this is the right answer here? Do you think this is the right equation of the tangent line? So type in a Y or an N or a yes or a no or a C or a no. I don't care what language you do it in. I can say yes or no in a bunch of languages. Tell me what you think. And then when I tell you to hit enter. Okay, ready? 5 seconds. 5, 4, 3, 2, 1, go. Thalia is the one holdout. It depends. All right, everybody except Thalia. Why do you think it's the right answer? Somebody give me a reason. Because I did it. All right, Brandon, thanks for saying, because I did it. Yeah, so you're going to trust the authority. You saw all the work. You believed every step. And so it stands to reason that it's right. Okay. Has anybody ever seen me make a mistake? Anybody? Yes, thank you, Jesse. Yeah.
Oh, I did too.
Yeah, okay. Yeah, I make tons of mistakes, all right?
I was gonna say, because I think you wrote the 6th when today's the 5th, I believe.
Hey, there you go. Good example. Yeah, today's the 5th, not the 6th. Okay, so even though, you trust me because I'm an expert, you shouldn't always take the expert's word for it, right? It's a great life lesson. So how can we check this? Well, would you like me to show you a way to check it? Anybody? All right. So this is how I would check it. So let me share with you. Let's see. Do I have a browser open? Sure. So we're going to go to my favorite graphing tool, online graphing tool. And that's Wolfram Alpha. You could do this in any number of ways. Oh, look, it's even blown up. So what I want to do is I want to plot my function 1 over x and my tangent line, which I think was 1 or y minus 1 equals minus 1 times x minus 1. But I'm going to add 1 to both sides here, just in case Wolfram prefers that. And I was interested at the tangent line is supposed to be at the point 1, 1. So let me go from x equals 1/2 to x equals 3/2. So the number 1 is right in the middle of that. By starting at 1/2, I'm going to miss the vertical asymptote there. And let's see what happens. You know what a tangent line is supposed to look like. Let's see if this looks right. So hit enter. I think it's thinking. It looks like it's thinking. Yeah, it's making thinking looks. Well, it got the what? That is weird. That is weird. Let's try again. Why it's getting x squared. There we go. That's better. So it's plotting these two functions on that interval. That's good. There we go. So down here in the legend, you see the blue curve is the graph 1 over x, which we expected because it's got a little curve to it, a little bowing to it. And then the purple curve is 2 minus x, which is a simplified formula for the tangent line. And you see there, or what I put in as a tangent line. Does that look like it's tangent at x equals 1? Yeah. So this convinces me that the graph is right. So from a student's perspective, when I was learning this kind of stuff, I'd come up with a tangent line and then I'd try to plot it to see if it looked like it was doing the right thing. And this one looks like it's doing the right thing. So this is evidence to me. It's not proof, but it's evidence to me that I got the right answer. So I'm going to go back to my iPad. So with that evidence, oops, my iPad went to sleep. With that evidence, I feel confident that my work here is good and that I don't have to go hunt down any errors, right? And this work here is the proof that this is the tangent line. Okay, this is the mathematical proof that the tangent line to this curve at this input value is that. So if I never made mistakes, I'd feel pretty confident without having to look at a function or a plot. But as I'm learning this stuff, it's good to get some like a second opinion. All right, so we're at 8:44, 6 minutes until a break. Let's do this for another function. So this is what I want you to do. Let's find an equation of the tangent line. It'd be good if I could write legibly tangent line to y equals x squared at x equals -2. So I'm going to ask for people to help me out in these steps. Okay, I'll go through the steps and I'll ask for people to throw into chat or to vocalize some assistance in this process. So I'm going to write scratch work here again, just to let everybody know, the universe know that we're writing down stuff that can look messy and can look ugly. So what form should the tangent line take? What form do I want to use? Can somebody tell me what that is? What form do I want to start with? What general form do I want to use? Yeah, Jesse. So the graph of this thing looks like a parabola. I want to sort of start with an equation for a tangent line. So what equation for a line? Yeah, so linear. So what formula do I want to use for that linear function? This one?
They put in a chat.
Yeah, I see.
Oh.
So why not this one? This is not the, Andre put in point slope, and Andre is right. This is another formula for the for a line. Why don't we want this one? It's got slope in there, right? It's a good question. Here's the point slope form. Why is this one better? It's better because it's easier. We have this information. We can plug that in. This is not better because we don't have that information. Okay? So we work with this formula for a line because it's easier. Okay? And easy is always a good way to go in mathematics. So for us, what is x naught? Anybody? Throw it in the chat. Thanks, Robert. It is -2. Somebody else? What's f of x naught? Which is y naught? Yep, Jesse, it's 4. Very good. So we know our line is going to look like y minus 4 equals slope times a quantity x plus 2. Right? And now we just have to find that m. And this is where we look to seniors Newton and Leibniz. Okay? And they tell us m in this case, I'm going to say the slope of the tangent, is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. Okay, so what do we have to do here? Well, we just have to keep cool and remember we know what x naught is, right? We have x naught. It's -2, so we can throw that in there, right? And it's right here too. And we know what f is, right? We've got a formula for our function here. And so we can do that. So let's do this in 2 steps. It's always good to do things one at a time. And after I do this, we'll take a break. So x naught is -2. So I'll sub that in. And I get that. And the last thing I'm going to do before we take a 5-minute break is use the formula for our function. And that's our function is the squaring function. So I'm just going to write that square in there. And after the break, we'll finish this computation. So one thing you could do during the break is do the computation and see if your work matches the work that we do as a group. There's something I said I was going to do over break. Oh, I was going to look and see what learning target D4 was. All right, I'm going to do that. And I'm going to start my timer. Give us a 5-minute breather. Get some coffee and stuff too. All right, so I'll see you back here in 5 minutes. And I'll turn on music again. Okay, it started again. Unless somebody wants to see me use Wolfram Alpha again to do this, I think I'm just going to move on.
1 second. I actually had one more question.
Yeah, Alexia.
Sorry. So the part where you squared the -2 plus h, so I noticed in the last problem also, so you basically bring the, you use the y equals x squared or whatever it is, the last problem was 1 over x.
Correct.
So then you're putting it into that form.
Correct.
Okay. So that's
Yeah.
gonna be for all of them we use. It will be something different next time, but
Yeah, right. So here in this example, f of x is x squared, right? That's the formula for my function. And so from the step at the bottom of the page down here to up here, I'm changing from the abstract symbolic f to the symbolic formula for f.
okay.
Right. I'm plugging in, taking this input and plugging it in to my function here.
Okay. All right.
Okay.
Okay.
Yeah,
Got
good
it.
question. And then Selena, I saw you have a question in the chat. What does H stand for? You're talking about this H right here? No, the other one. So which H? You're, like this, the H's that are in the formula? Okay, so good question. The H's that are in the formula are the same as this H. Okay, so that's the first thing you need to know. It doesn't answer your question, what does it stand for, right? Symbolically, the H's in the limit are the same thing that are as part of that limit. So I'm gonna scroll back for a second and show you a picture. So look at this picture here in the top left corner. We've got X as an input, and we also have X plus H. So in the picture, H is this distance between these two inputs. H is the horizontal distance between the 2 points that are defining our secant line. That's what I want you to think of H as. And so as H gets smaller and smaller, this new point gets closer and closer to the original point, the point of tangency. So in this picture here, our H is positive, but it could be that H is negative and X plus H could be over here. And then the secant line's on this side, and it approaches the tangent line from a different way. But what I want you to understand, your answer to your question of what does H stand for, H stands for this distance, the horizontal distance between these 2 points that make the secant line. Is that good? Does that answer your question? Okay. Do we want to do one more example of finding the equation of a tangent line using the Leibniz Newton approach? Anybody want another one? Okay, let me give you one more, and this is kind of an important one too. Before I start it, let me just point out that I did what I said I'd do over break, and I looked at learning target D4, and it's about differentiation rules and thinking of them as theorems. And so we'll definitely start that next time if we don't start talking about it today. And I put parenthetically what those differentiation rules are: the constant multiple rule, the sum difference rule, the product rule, the quotient rule, the chain rule. Some of those titles should look kind of familiar. All right, so let's do this example. Let's find the equation. The equation of the tangent line. Okay, here, I'm going to put a line. Here's an equation of a line. So it's a linear function. Find the equation of the tangent line to a linear function at, anybody want me to use a particular input? Anybody have a favorite input they want? Throw it into chat. First one gets it. Anybody have a favorite input? 4. Okay, Robert's got it. 4. Okay. So we're going to do this the same thing that we've just been doing, except here this is what's the word? This is an abstract function, right? M is some parameter, B is some parameter. So I'm representing all non-vertical lines by this equation. So I should be able to find the equation of a tangent line to any linear function we choose. So we'll start out in the same way. Let's do scratch work. So we're going to do the point slope form. Let's, I'm going to put the subscript on there so we know it's different from the M that's in the given function. So in this case, X naught is Robert and Athalia's X naught equals 4. And what's Y naught? Well, Y naught is f of X naught, which is f of 4. And so in this case, it looks like it's 4m plus b. Okay, so let's just write that down. This is kind of messy, but that's okay. So that's what we have for the equation of our tangent line so far. But now we need to figure out what the value here is. So we're going to use the Newton-Leibniz approach. The slope of the tangent line is the limit.
Dr. Miller?
Yeah.
I think you plugged it in incorrectly. Your X naught and Y naught.
You think I plugged it in incorrectly? What do you think it should be?
Well, your Y naught is 4m plus b, correct?
Yeah.
And then you plug that in where your X naught is at.
Oh, good. Good catch. Thank you. I totally agree with that. I did it backwards. Good catch. Okay, so that's what it should look like. So now when you calculate the slope of our tangent line, that's the limit as h goes to 0 of f of x naught plus h minus f of x naught over h, right? This is the standard definition. And so now our x naught is 4. So I'm going to put that 4 in there. And so next I'm going to use the function. So this is going to take a little more space. So I'm going to move on right on the diagonal. So if I plug in 4 plus h for my x, I'm going to get m times 4 plus h plus b. And now I'm going to plug in 4 for x. So I'm going to get m times 4 plus b. Okay. And in the first term, I can distribute this m across and I get 4m plus 4h plus b. And I distribute this minus across the terms in that parentheses, and I have a minus 4m and a minus b. And what you'll notice here is we get cancellation. So what jumps out to me first are the b's cancel. And then I look here, I see I've got a minus 4m. Look at the term with the m's in it. Oh, there's 4m. So these are going to cancel too. So I'll do those in a different color just to emphasize where the cancellation happens. And you'll see here I'm left with 4h. And there, you see I get some more cancellation. The h in the denominator cancels with that h in the numerator. And so I'm just left with 4. And the limit of the constant is that constant. And the slope of my tangent line is 4. So plugging that into my formula, I get y minus 4m plus b equals 4 times x minus 4. Okay, so that's the answer. Now, this isn't something that we can really plug into Wolfram Alpha because of these abstract parameters. It doesn't do too well with those symbols. So Brandon threw in a question. Shouldn't it be m times h after distributing? Oh, yeah. Oh, yeah. Good catch. Not 4. I was distributing the wrong thing. So you're saying, Brandon, that has to be an m. And that here, that had to be an m. So we're not left with 4. We're left with m. Well, that's interesting. That's interesting indeed. So the slope of our tangent line is the same as this slope. Well, that's kind of cool. So slope of our tangent line is that m. Let's look at something else. So I don't have much room here. Copy. So I'm going to go to the next page. So here's what we just calculated. And I'm going to write down where we came from. Y equals mx plus b. So let's simplify the equation we just came up with. Okay. And let me add 4m to both sides. So the left-hand side becomes y minus b, and the right-hand side becomes mx. If we add b to both sides, I get that. So what does that show? Yeah. These are the same. These are questions, these equations describe the same line. So geometrically, what that would mean is that if I have a line that looks like this, and we have a point on that line, if somebody asks you what the tangent line is, well, the tangent line will always coincide with the original line. The tangent line to a line is the line. That should make total sense geometrically once you draw the picture. And the cool thing about this example is that it all works out algebraically. And in fact, if our input had been symbolic too, it would have all worked out just fine, right? We would have seen that the slope of the tangent line was the original line. So a very important example when we understand derivatives. And here we just worked it out in the special case where the input was 4. Okay. All right. So let's talk about some concepts. And then I want to do a couple examples that help us. I think going back to D3, one of the things that you need to be able to do is I give you a graph of a function and you need to be able to sketch its derivative. So we'll end class that way. But what I want to do is I want to talk about differentiability. So here's a definition for you. A function f of x is differentiable at x naught if f prime of x naught, which is the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h exists and a lot of people say is finite. Okay, so if you get an infinite limit, we're going to say the function is not differentiable. Okay. So here's another definition. A function f of x is differentiable on an interval a, b in its domain if it is differentiable at every x in that interval. Okay. So here's the definition of being differentiable on an interval. So some time ago, we studied the property of continuity. And continuity is a property of functions, much like differentiability here is a property of functions. In fact, our definition of continuity kind of parallels this definition we have for differentiability. We define continuity at a point first, and then we defined it on an interval by saying its function's continuous on an interval if it's continuous at every point. So in some sense, differentiability here is paralleling the way we're thinking about continuity. Both are defined at a point. Ultimately, they're defined at a point. In our conversations about continuity, we learned how to recognize from a graph if a function is continuous, right? We learned that a function is continuous at a point if it's defined at a point, if the limit of the function at that point exists, and if the value of the function equals the limit of the function at that point. So, and then we know that that means that the function doesn't have a hole, it doesn't have a break in it. So we have a geometric interpretation of what it means for a function to be continuous. Now I want to have the same conversation or the analogous conversation with you about differentiability. Okay. What does this tell us about the graph of f of x? If a function is differentiable, what does that tell us about the function? So everything hinges on this definition. So I'm going to write that up here. I'm going to write it in blue. The limit as h goes to 0 of that difference all over h. So what I want to point out to you is if this exists, then the limit as h goes to 0 of the numerator has to be 0. If it's not 0, then this limit here is undefined. It goes to infinity. It's an infinite limit. So for this limit to be finite, the limit of the numerator has to go to 0. But by our limit laws, that means that the limit as h goes to 0 of f of x naught plus h equals f of x naught. Okay. Put the, ultimately, this means f is continuous at x naught. Okay, so this is a theorem, and it requires some proof, and this is what I have shown you here is not a proof, but the theorem is this: if f of x is differentiable, and I'm going to abbreviate here, at x naught, then it is continuous at x naught. And a corollary to this is the following: if f of x is not continuous at x naught, then f of x is not differentiable at x naught. And I'm sorry, I'm so low on the page. Okay, what I just wrote here, this corollary is a logical corollary, and it uses a property called contrapositive. I won't talk about it in any detail, except to say that it's obvious. It follows immediately from the theorem. And what it tells us is that if I give you a graph and ask you, where is this function not differentiable? The first things you look for are points of discontinuity. If there's any place the function is not continuous, it's automatically not differentiable there. Okay, that means it doesn't have a tangent line there. Right? So you can't talk about the slope of a tangent line if it doesn't have a tangent line. So let me give you just an example. So suppose I've got a function that is discontinuous. It's got a point discontinuity. And I ask you, what's the slope of the tangent line there? Well, it has no tangent line because the point of tangency isn't part of the graph. Okay, no tangent line. Let me give you another example. A jump discontinuity. So I ask you to find the slope of a tangent line at x naught to this graph. And you say, Miller, I can't because it's discontinuous. And I say, what does that have to do with anything? And you say, I can draw an infinite number of tangent lines at this point, and none of them make sense. Right? So you could draw an infinite number of tangent lines there. Or it turns out if you did the limit definition of the derivative, you'd see immediately that this doesn't exist because the one-sided limits don't. They disagree. Okay. So if a function is discontinuous, it can't be differentiable there. There's no tangent line, so you can't talk about the slope of the tangent line there. But it turns out that there's another way for a function to not be differentiable. And it falls under this umbrella, that the one-sided limits of the slope of the tangent line don't agree. Okay. And so differentiability needs more than continuity. It needs smoothness. Okay. F prime of x naught is the limit as h goes to 0 of the slope of the secant lines. Okay, that's what that formula means. Okay. If the one-sided limits of these slopes are different, the graph is pointy. Right? It has an edge. It's got a sharpness to it. And that's a place where the derivative does not exist. So let me draw for you an example. First, I'll start it here. It's a cusp. And I think my favorite example of a cusp is the graph. I think this is the graph y equals x to the 2/3. So cusps are pretty easy to draw. They're pretty common. Here, let's say what Wolfram alpha says a cusp is. So we're going to plot x to the 2/3 on x minus 1 to x equals 1. Oh, typo. X equals -1 to x equals 1. Oh, Wolfram Alpha could only draw half of it. All right, so sometimes life is complicated. This will fix it. So there's an example of a cusp. Okay, and you can see here it's pointy, right? The graph, there's nothing smooth about the graph right here. It comes to a sharp edge. So let's see, how can I do this? I should have done this on my iPad. Let's see why the limit definition fails. So let's go back to my iPad and I'll do a cartoon of a cusp. Sharing, okay. So here's our coordinate axes and here's a cusp. Looks like a bird's beak, right? Oh, that was bad. Right, so the function fails to be differentiable here at 0 at the pointy part. So what's happening? Well, if you take secant lines to the right, all of these have positive slope. Okay, and if this is 0 plus h, as h gets smaller, the slope grows. And I think you can be convinced that it grows without bound. That tangent line gets steeper and steeper and steeper. On the other side, oops, if your h is negative, your secant lines all have a negative slope. And as h goes up to 0, they grow in size without bound. So they're getting more and more negative. They're getting bigger and bigger in the negative direction. So the limit as h goes to 0 of the slope of the secant, or if it goes from 0 from below, cannot equal the limit as h goes to 0 from above of the slope of the secants. Therefore, f prime of 0 does not exist. Okay? F of x equals x to the 2/3 is not differentiable at x equals 0. Okay, because the limit as h goes to 0 of the slope of the secant lines doesn't exist. Okay, and it's because of this pointiness here. So online, I've got a couple screencasts that I would like you to watch before class on Wednesday. One is about the absolute value function. And the screencast shows you that the absolute value function is not differentiable at x equals 0, right? Because the absolute value function is pointy there, right? So I want you to be able to explain to me and anybody else why the absolute value function isn't differentiable at 0, and the screencast will show you that. There's another screencast that's titled Differentiability. Implies continuity. Okay, and it concerns this idea that if that the derivative exists at every point on an interval, then the function has to be continuous on that interval. We already convinced ourselves that for a function to be differentiable, it has to be continuous, but this screencast puts a little bit more meat on those bones. All right, we're at 9:32. Let me recap where we're going. So D3, I wanted to talk about the derivative as a function, and I've done that. F prime of x is defined to be the limit as h goes to 0 of f of x plus h minus f of x all over h. In class today, as we've been talking about it, most times that we've brought this up, I've had a little subscript there, but the input doesn't matter. It works for all input. So that's why we define this as a function, right? And this is the function that takes x to the slope of the tangent line of the graph of f at x. So this is the definition of differentiability. I've talked about how to recognize when a function is differentiable and when it's not differentiable. It's not differentiable wherever there's a jump, where there's a discontinuity, or where there's a point. So I want you to think about, what does that mean for all the families of functions that we have? Which families of functions do you think are always differentiable? Which ones are differential some places? Which ones are differentiable no place? So that's a good exercise to connect the idea of differentiability with what you know about families of functions, because we can always use some more practice in making connections between these ideas. The last thing I want to tell you about today for D3 is how do we look at the graph of a function and then sketch a graph of its derivative. So what I want to do is this. So this might take me a second. So I'm going to show you how I do this. It's going to make some sausage. I want to share Wolfram Alpha so I can get a graph of a function. Anybody have a function they want me to plot to look at for differentiation? We have a favorite function. Anybody? Just not a linear function, because those are boring. We know the slope. Well, we could do a linear function, but x cubed plus 7. All right. So let's plot x cubed plus 7. Let's see if it looks interesting from x equals from -1 to 1. Let's see. Yeah, sure. All right, so what I'm going to do, that doesn't have, well, I'm going to take a screen grab of this. All right, so I just took a screen grab and I'm going to see if I can send it to my iPad easily. So pardon me while I dig through my file system here. I've got this. Almost got it. All right, so let's go back to my iPad. I'm going to try to import the screenshot. All right, so here's the graph of x cubed plus 7. Oops. X cubed plus 7. And we want to graph or sketch a graph of its derivative. Okay, so this is f of x. Sketch f prime of x. That's what we want to do. So what we're going to do is we're going to go and pretend we're learning about functions for the first time, and we're going to make a table of values. So I'm going to pick a bunch of values to put in to the derivative, and I'm going to estimate the outputs of the derivative. So I'm going to do that here up at the top. I'm going to say, here's my list of x's, and here's my list of x or f primes. So here my table of values will go right up here. And I think the values I want to put in are going to be negative 0.5. Let's start with these, negative 0.5, 0, and 0.5. Negative 0.5, 0, and 0.5. So just let's start with negative 0.5. So I'm going to go to negative 0.5 here, and I'm going to look to see the point that's on the graph. I'm going to mark it. And then what I'm going to do is I'm going to sketch the tangent line. It's not a perfect sketch, but it's a pretty good sketch. And now I'm going to estimate its slope. So let's do this. Well, I drew it long enough. Here, let's come all the way down here. So I can come up from -1. So I have that point right there, and we can come up to 0, and I get this point right here. So input is -1, input is 0. So now I want to figure out what's the output here. So I'm going to come horizontally. Looks like we're at about 6.4, and up here we're about 7.4. Oh, that's pretty good. 6.4 to 7.4, that difference is 1. So the rise of 1 over the run of 1 tells me the slope is 1. So let's write that here. The slope of that tangent line is 1. Okay, so I put that value in my table of values. Now let's look at x equals 0. So at this input, I come up and I find my point here. I'm going to mark it in black. And then I'm going to draw the tangent line. I'm going to do it in a different color so I can kind of keep everything straight. My dog's trying to get in my room. So that's the tangent line. And if I'm not mistaken, that tangent line looks pretty horizontal. But let's just double check. So I'm going to look at the input here at -0.5 and the input here. Right? I'm going to look at the rise over run. So this rise looks like it's at 7. This rise also looks like it's at 7. So the rise is 0. So a rise of 0 over any run, I'm going to have slope 0. So this line looks like it's got slope 0. So I'll fill that in the table. The slope of my tangent line at 0 is 0. All right, let's go back to the process here. Put the input of 0.5. Let's go up to the graph. I get this point. Let's mark it. And let's draw the tangent line here in a different color because I can. And let's estimate the slope of that tangent line. So I'm going to pick 2 points on that tangent line, here at 0 and here at 1. So at 0, it looks like my output is at 6.7. At 1, my output looks like it's almost at 7.7. Let's say it's 7.7 and my sketching is bad. So rise is 1. My run is 1. So my rise over run is 1. So now I have 3 points on the graph of my derivative. So let's plot those points. And I'm going to plot those points in blue. Okay. So I have the point negative. Oh, geez, we can't see it on the graph because they start at 6. But let's say that this is 0.5, and this is 1.0, and this is 1.5, and this is 2.0. Okay. So for the y-axis for the derivatives, so at negative 0.5, my y value is 1. At 0, my y value is 0. At 0.5, my y value is 1. Okay, so these are 3 points that are on the graph of my derivative. Now, if I was really lazy, I'd say, well, let's just connect these lines like this. And this is a real lazy estimation of my derivative, this light gray V. But if you're a little more subtle about looking at the graph of the original function, what can you do? Well, if I move my input from 0 over to 2.5, say, and I got this point right here, it looks like my tangent line is still pretty flat. And so its slope is going to be positive. I can see it's going to be positive, but it's going to be pretty small. So the graph is probably actually lower. And then as my curve gets, or as my points get closer and closer to the input of 0.5, the tangent lines are getting slightly bigger and bigger. So I think a better sketch of my derivative would look like this. I'm going to draw it in broken curves like this. And then you can also notice that as your inputs get bigger and you take points further and further out on the graph, the tangent lines are getting steeper and steeper too. And so I think it's probably fair to write or sketch the derivative looking that way. And a similar thing would happen on the left-hand side. So those dotted lines would sketch for me the graph of the derivative. So this is how we go from the graph of a function to a sketch of the graph of its derivative. You start by drawing tangent lines to the original graph and then plotting the ordered pairs that are input, comma, slope. Input, comma, slope. Input, comma, slope. Okay. So the y values of the derivative represent the slopes of the tangent lines to the original function. If you wanted to, right, you could pick another intermediate input point of the graph, draw the tangent line, and estimate the slope from the graph or from the coordinate axes. That's perfectly legit. But this is the shape for this example that you're going to come up with. Okay. And in fact, pretty soon you'll learn that the derivative of this function is actually 3x squared. Right? The derivative of x cubed plus 7 is actually 3x squared. So this is the next thing that you have to be able to do, be able to look at a function and see its tangent lines and be able to estimate the slope of its tangent lines well enough to make a reasonable cartoon sketch of the function's derivative. And the most important tangent lines to be able to pick out, and the ones you should always start with, are those that are horizontal. Those are really, really important. And here we saw that there was one, that there was a tangent line that was horizontal. Should I, let's see, we're at 9:45. Should I do another one? Yes, I should. I'm going to. Oh, come on. Oh, I see what you're doing. Sorry. Oh, come on. So I'm going to just make this one up now. So suppose we have coordinate axes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2. And these aren't totally uniform. And let's suppose we've got a graph that starts here, goes up, comes down, and goes back up. Let's sketch the graph of that curve. Sketch the graph of the derivative of this curve, I'm sorry. Okay, so you look at it, and we know that we need to make a table of values for inputs and the slope of the tangent lines at those inputs. And I told you that the tangent lines you really should pay attention to are those where the slope is 0. And you can kind of see we have one right there, and you can kind of see we've got a tangent line with a slope of 0 there. So you're interested in this input that's right here, and we're interested in this input that's right here. So I'm going to call that one of the first input is 2 1/3, and I'm going to call the next input 5 6 6 2/3. And if you draw the tangent line at those points, you'll agree that they're horizontal, and so those slopes are 0. Those slopes are pretty easy to calculate. Easiest slopes to calculate ever. And then it's just kind of dealer's choice. You get to figure out, choose whatever inputs you want to. So let's choose 1. Let's choose 4. And let's choose 9. Yeah, and see what we get there. So we'll use orange. So at 1, I get this point, sketch the tangent line, make it big enough so I can draw a good triangle. And I'm going to draw a triangle here from 0 up to 3. And so I'm going to estimate that at 3, I'm at that point, and at 0, I'm at that point. So my delta x, my horizontal distance, my run is 3. What's my rise? Well, it looks like up here I'm at about 7, let's say 7 1/3. And then down here, it looks like I'm at, wait a second. Down here, it looks like I'm at 2/3. So I'm going to say, let's do some scratch work here in gray. Delta y is, what did I say? 7 1/3 and minus 2/3. So that's 22/3 minus 2/3. That's 20/3. So that's 6 2/3. So that's, well, we don't need this last one. I'm sorry, that's so low on the page. So delta y is 20/3. Delta x was 3. And so our slope at 1 is 26ths, or 10/3, or 3 1/3. All right, let's play the same game with a different color. We'll do dark green at x equals 4. So here I'm doing this input, go up to the graph, I get this point. Okay, so I'll sketch the tangent line, make it nice and long. So I'm going to look at a triangle. So it looks like we got a nice intersection here at 6. So let's go down to 2 here. We'll go up. So I get this point. So it looks like that point is right about, I'm going to say 6 2/3. So doing some more scratch work, delta y is 6 2/3. On one end, on the other end, I said here it's going to be 0 at 6. Now I got to be careful. My delta x, I started high, so I'm starting down here. So my delta x, right, was I at 2? I think I was at 2. My delta x is 2 minus 6. So 2 minus 6 is a minus 4. So my slope at this point is 6 2/3 over minus 4. That's 18, 19, 20/3 over minus 4. That's 20 over minus 12, which is minus 10 over 6, which is minus 5 over 3. Okay. So here I'm at input 4. Slope is minus 5/3. Oh, and I'm over time. So let me just finish by saying, and I'll do this in red this time. So what I figured out at 1, I was at my slope was at 3/3. So my tangent goes through that point. It goes through this point. Let's get rid of these so we're not confused. At 4, my tangent goes through -5/3, or my derivative goes through -5/3, and then I said here at 0, and my dog is. So if I were to string these together, I get a derivative that kind of look like that. Kind of look like a parabola. Okay, but I'll stop there. We're over time. If somebody reminds me, I can maybe finish saying some things about this function and this process. But that's it for today. Sorry I went over. Thanks, everybody. Take learning target quizzes. Watch for a grade report. Come to office hours. I will see you all on Wednesday. Hi. What's up, Lupe?
No. Is there gonna be an assignment or something next?
Yeah,
next
I'm going to
class?
try to have an activity for the group to do next time. But one of the things I'm trying to figure out to do is how can I? Is there a way I can have students sketch tangent lines like I was doing? Right, that's what I'm trying to figure out. And there's yeah, I'm not sure. I
Yeah.
think on the so there, have you seen these Google Jamboards before?
Jamboard sounds familiar.
I think there might be a way to do that. So I'm gonna look into that. I think I can make a Jamboard and I can put a graph on it, and then I can have the students sketch tangent
Click on
lines
it.
on them.
Yes.
But so watch for an email from me. I'll try to work that up this afternoon. But it's just to get them to plot points, do what I was doing in this last example, plot
Mm.
points. So thanks for asking though. It's on my mind. I'm trying to figure it out.
Mm.
Okay. I'll see you on Wednesday.
Okay.
Bye-bye.